Dear friends, in the series of learning aerodynamics, in this class, let us discuss about how the that means minimum velocity at minimum drag is achieved, and how the stalling velocity is different from the that means velocity at minimum drag. So this thing I will discuss. So first of all, we know that the drag equation d equal to av square plus b by v square, because we know what is a and b are constant. Those a and b are nothing but a equal to cd naught of rho s, then whereas b equal to 2k w square by rho s. So this is what about constants a and b. So that means the velocity, the drag is a function of only the velocity, because the rest of the parameters will be constant. So drag is only a function of constant velocity. So that is what here we are representing, drag versus velocity. Vertical axis is drag, horizontal axis is velocity. So now okay, because we are representing this drag equation in this graph, so this is nothing but we can say as the this one is nothing but this is proportional one directly proportional to v square, then whereas this is inversely proportional to v square. So that means, yeah, so this is okay, so this is okay, increasing, that is this is nothing but zero lift coefficient, then whereas this is nothing but induced drag coefficient. So the zero lift coefficient increases with the square of the velocity, whereas this one decreases with the that means inversely proportional to the square of the velocity. So this is what, okay, from the drag equation we are seeing. So in this we just know that this is nothing but total drag. So this curve represents the total drag. So here how, okay, because the total drag, okay, here that bottom, this one, this bottommost, this part, okay, will represent the minimum velocity, that means lowest velocity for the minimum drag, and this component, this, okay, we can say as the this component, all okay, this edge line represents the stalling velocity. This edge line from, okay, this point and this point, so all of them, okay, represents the stalling velocity. So even in this graph we can say this is the stalling velocity, so this is the v stall. So we know stalling velocity is the lowest velocity at which the aircraft can sustain in the air, because below the stalling velocity aircraft cannot sustain. That is what okay, from the theory, or okay, that is what we have to understand. So okay, and we know the stalling velocity and this velocity at the minimum drag are different, because stalling velocity is here, and this one is the minimum okay, drag velocity, and this is stalling velocity. So stalling velocity and minimum drag velocities are different, and also the stalling velocity is lower than the minimum drag velocity. So that is what here we are seeing, because stalling velocity we are achieving at a maximum lift, because v stall is achieved, we know v stall equal to square root of the 2w by s rho cl max. So this is what, so this component is responsible for achieving the v stall. So v stall we are achieving this, so this component we are achieving with the help of cl max. So means we can't say at that point the drag will be minimum. That is what here from this curve we have to understand, because as we know that cl alpha curve says that as the lift increases, drag also will be increasing. So we know that this is okay, so this is the cl alpha curve. So here what, this is what, okay, we achieve that means CL max. So CL max, this is CL, so this is alpha. So this CL max we are achieving at this point. So it means as long as lift increases, the drag also will be increasing. So that is a consequence, because that cannot be avoided. So but we can minimize, we can, that increase in drag can be minimized. So that is what we used to try in many ways. So minimum drag, or okay, that means CL max, maximum lift coefficient is achieved at the okay, what to say, highest angle. So angle of attack, when the angle is high, that time we are achieving. So that time drag also will be higher. So that is what in this graph we are seeing. As we are seeing the, that means stalling velocity from this graph, and we see that drag also is okay, slightly okay, drag also is considerably higher. So it means the drag cannot be, the drag, okay, this component cannot be neglected, or okay, this drag cannot be taken as minimum. So drag will be there, drag quantity will be considerably okay, considerable quantity at the stalling velocity. So that is because of the increase in lift. So that is one thing. And another thing is stalling velocity is smaller than the minimum velocity, that means velocity at a minimum drag. So this is okay, if you want to find out what is the velocity at a minimum drag, that we can obtain from this equation, because if you differentiate this equation, we will get the minimum velocity for minimum drag. So we can just find out from this, and then we can just see here. So for finding the minimum drag, for finding the minimum drag, so we have to differentiate this equation. So okay, that is nothing but dD by dV equal to 0. So if you are differentiating this equation, we will be getting the velocity at a minimum drag. So 2AV plus okay, this is okay, we are just bringing to numerator, so it will be minus 2 into B V minus 2 minus 1, so nothing but minus 3. So this is equal to 0. So we can just further simplify. This is 2AV equal to, this we can take it to other side, 2B V cube. So that is okay. So 2 will be cancelled, and we can AV, this is okay, we can even, this can be written in denominator B by V cube. So V cube into V, that is V power 4, so B by A. So this is, so then V equal to B by A whole power 1 by 4. So this is what, okay, about velocity minimum, that means velocity at a minimum drag. So this we can see as the minimum drag velocity. Minimum drag velocity equal to B by A whole power 1 by 4, because we know what is B and A. So those, by substituting those constant, then we can obtain this minimum drag velocity. Also we can find out the CL minimum drag and the CD minimum drag. CL minimum drag, we can just use this equation, because CL minimum drag, okay, just we got the velocity minimum drag. CL minimum drag also we can find out, okay, that is, we can use this formula, that means drag equal to, so we know that is nothing but drag into lift by lift. So in steady level flight we can write, okay, steady level flight, this can be replaced in steady level flight. So it can be replaced, this is, we can replace with W. So drag equal to drag into W by L. So this is, we can just modify W into D by L. So for obtaining the minimum drag, this component, if you want to have a minimum, then this component should be minimum. So that is what the idea. So that means drag minimum equal to, so drag minimum equal to W into D by L minimum. So this is, we can drag and lift can be replaced in terms of CD by CL, because we can express both numerator and denominator, that drag expression and lift expression, then we can cancel out. So this CD drag by L, we can change into CD by CL. So this is minimum. So when drag minimum, this is. So then by substituting, this is further can be expanded. W into the CD is nothing but CD naught plus KCL square by the CL. So this, for obtaining the drag minimum, now okay, we have to differentiate. So for obtaining the drag minimum, so as drag minimum, the differentiation of drag minimum divided by DCL equal to 0. Then differentiating that, okay, by using U by V formula, then we are obtaining what is CL. So CL equal to CL minimum drag, we are getting square root of CD naught by K. And then CD, okay, we can substitute in this equation, our drag polar equation, then we will be getting CD naught plus CD naught, because CD naught equal to, the KCL square is nothing but CD naught. So by replacing that, we will be getting this. So CL minimum drag and the CD minimum drag can be obtained from this expression. Also that means we got the minimum velocity, that means velocity at minimum drag. So that also we have seen how to obtain. Then another one, final drag, total drag we can obtain. Total drag we can obtain by using this formula, because we know CD equal drag minimum equal to W into CD by CL. This is okay. So minimum. So in this, we know the CD minimum and CL minimum, we can substitute and we can get that W CD is nothing but 2 CD naught by this K. CL is nothing but square root of CD naught by K. This is. Then this further we can simplify, W into CD naught. This is 2 CD naught. This we can bring it to reverse it. So we will get a square root of K by CD naught. So now okay, this further can be simplified. Drag minimum equal to W into 2 CD naught. 2 will be there, and then CD naught, we can express CD naught into CD naught, then square root of K by CD naught. So this one CD naught will be cancelled out. The remaining will be 2W into square root of K into CD naught. K into CD naught. So this is what drag minimum. So drag minimum we can obtain by using this expression. So we got all the expression, that means we got the CL minimum drag, CD minimum drag, and also total minimum drag equal to what. So this is also, we have to understand that it is not function of, it is not the function of that means or we can say that minimum drag will not be affected with respect to the altitude parameters, and either we don't have a density or we don't have any other parameters, okay. So to take it into account, that means as long as it is flying at the steady level flight or it is in the one particular altitude, this minimum drag will not be affected. So minimum drag don't have any linking or don't have any relationship with the altitude. As the altitude remains constant, minimum drag can be will be constant. Also minimum drag is not the function of density, so we can't say that minimum drag will be changed or will be affected because of the altitude. So that is